Hello and welcome everyone to Arabidal, a show where we look how a Trackabidal database is implemented internally, where we learn how you could use Zeek to implement a highly reliable distributed database, where we learn how you could manually manage memory in such a way that you don't actually have to manage memory at all, but you allocate it once at a startup and then it sits there and never needs to be freed, never needs to be allocated more. Okay, so let's dive right in. As usual, we'll start with a little recap of the previous episode, because that was actually like one of the keystone episodes, and then we'll continue to the new topic. So last time we were talking about preset, specifically what happens with a free set when we approach a checkpoint. So, as a reminder, Trackabidal is a database. So, it stores the actual data in a data file. And when a Trackabidal process starts, the first thing it does is that it opens this data file, reads data from this data file, and this data forms the basis of what is there in the database. Internally, the data file organized as a persistent data structure. So essentially, it is subdivided in many small blocks, and blocks refer to each other with the address and a checksum. And there is a root pointer stored in the superblock to the root node of this persistent tree. And you can think about the checkpoint of this root, the checksum of this root as a checkpoint. Actually, this kind of like logical, like checksum, checkpoint, they start with the same word, so they mean the same. Okay, so, and of course, data file has some parts allocated, but also some parts are free. So when replica iterates, it has this persistent data structure on disk, has some free space, and it writes an updated copy to the data structure to that free space without disturbing the existing data structure, because it might always be the case that replica crashes at any arbitrary point in time, and we want the replica to be able to restart and continue. And the idea here is that because you do not update the data structure destructively, if you crash and restart, you restart from the same checkpoint and just roll forward your write-ahead log. And then comes the actual process of checkpoint, where we swap the root pointer in the data structure, where we said, okay, so previous checkpoint was this checksum and this address of the root block, and now in the new checkpoint, like the checksum and the address is different. So let's like atomically swap those. And like atomic swap is implemented through writing multiple copies of a superblock. So one part of a checkpoint state is actually the bit set of blocks which belong to this checkpoint, the free set. And like obviously, like you need a free set to be part of your checkpoint state, because while you are in a particular checkpoint, you want to be preparing a new checkpoint. And as we've said, you have to use free blocks for that new checkpoint. So you need to know which blocks are free, and for that you need to know a free set. So when we come to the checkpoint boundary, where we need to do this atomic swap of root pointer, one thing we need to do as well is to write our free set to the data file, so that in the next checkpoint we actually start with a new free set. And last time we looked at how that works, and that is like pretty straightforward. First, we encode free set into compressed representation using ER encoding. And oh dear, let me try to reconnect to the stream. Give me a moment to, give me a moment to fix my internet connection thing. Okay, hopefully I should be okay. Yeah, it looks like I'm live again. Yeah, it's like football season, and apparently Portugal just bans all the streaming traffic during football matches, so that people do not pirate the games. And like we are trying to actually make this translation from Sweden, but again, even Sweden doesn't work today perfectly. Anyway, yeah, so at the checkpoint, we need to write free set, the set of free blocks, to disk. This is relatively straightforward. First, we encode, we compress the free set, which is a bit set, to get a compressed encoding. For that, we essentially use spiced up raw length encoding. Then we write the result to disk as a linked list of grid blocks. And then we stuff a pointer to the root of this linked list, to the first node of this linked list, into the superblock. The only fun thing there is, like, when you write a free set, you need to allocate some blocks for it, for the encoded, but are blocks which are storing free set considered to be free or not? And there is this fun Russell's paradox in that, if you allocate those blocks, you actually change the free set. So there is some nifty hackery around that. Anyway, so why was all this talk about the free set? Because free set is the key component that we need to actually start mutating data on disk. Because so far we looked at the data mostly statically. Now we want to mutate it. As we've discussed, we cannot actually mutate data. We need to keep data immutable so that we can restart the known safe state after the crash. So mutating data essentially reduces to allocation, because we allocate a free block and write new stuff into that free block. So the main component of our mutation is going to be compaction. compaction of the LSM trees themselves. Compaction is like very tricky. Like it's probably well, I mean, like I guess like the most like complicated part of TargetBittle in terms of like cognitive load and whatever is like consensus, because like consensus is just like, you know, very like, well, it's like a very simple mathematical formula, but if you change just a tiny aspect of this formula, then like the whole thing unravels, and it's like hard to keep this whole thing in your head. While compaction is like relatively straightforward in terms of like explaining what is actually happening there, but it is like very hairy in terms of the actual concurrency in the source code. Like the code is like hard to understand. So today is going to be a warm-up. Before looking at the compaction code for LSM3, we will look at the compaction code for ManifestLog, something Brian asked about a couple of episodes ago. So let's just dive straight into the source code. Let's change to our RNVidal directory and take a look here. Okay, so we want to look at the ManifestLog. And this probably needs some explanation, because like, by this time you have already forgot what the ManifestLog even is. So, okay, a little bit more of a recap, a little bit further in the past, like maybe, I don't know, 5 episodes back. So, the main data structure which is stored on disk is an LSM3. The atom of LSM3 is an LSM table. LSM table is essentially a persistent sorted array. Now, LSM3 is like a bunch of tables. And the trick is like how you arrange the tables, how you relate the tables with each other. The idea here is that you arrange tables in layers. So a layer is a sorted list of tables. Again, tables are sorted list of items. Layer is a sorted list of tables. Layer is a sorted list because all tables in a layer cover disjoint ranges of keys. So you could actually arrange table in a layer. And then you arrange those layers on top of each other so that your lookup is hierarchical. You first do lookup in the 0th layer, then in the first layer, and like if you found something, then that's the answer. Otherwise, you fall back to layers deep. And this is and this hierarchy is used to allow cheap mutation, because like to mutate data on some deep layer in the LSM3, you don't need to like go there and mutate the data. Rather, you just need to shadow this data in some upper layer. So this like whole mapping between individual tables and layers is stored in the manifest. So if we look at the manifest, we see that it contains an array of levels. I really hope it does, otherwise it would be embarrassing. Yeah, so manifest. Manifest contains an array of levels, and each level internally stores a sorted list of tables. Now, this is the representation of the set of layers in memory. On disk, those tables are represented as a manifest log. So the idea here is rather than encoding, rather than serializing this layered data structure, we sort of incrementally build it. We represent the data structure by a series of individual table add and table remove operations. Okay. Table info. Let's say it's not table info. Oh, well, maybe it is table info. Okay, yeah, so a manifest log is a sequence of those tables infos, and table info is a reference to a table, so a checksum and an address of its index block, and an event, whether we remove or add this table and to which level we add this table. So instead of like say, hey, level X is tables A, B, and C, we represent our manifest as add table A to level X, add table B to level X, add table C to level X, and then sometime later there might be, okay, let's remove table X from table C from level X and whatever. And again, this has like, you know, the same shadowing structure. If you want to remove table from a level, you don't actually need to like, you know, physically go and mutate this manifest. You can append just a single entry on top of your log, which says, hey, this table now is removed from this level. And herein lies the problem. If you mutate your manifest in this way, like your manifest actually grows unbounded. Like this, like the number of events just grows and grows and grows until you run out of disk. And that's problematic. The idea here is that we can run a compaction. So if in this login event of events, you have add table X to layer L, and then you have remove table X from layer L, what you actually can do is that you can annihilate those two opposing events and just remove it from the log. And that is the idea of compaction. So, okay, before we get to that, it's important to note that this sequence of events is the logical structure of the manifest log. The physical structure of a manifest log is, of course, a linked list of blocks on disk. And each block stores a bunch of events. So this is the idea of compaction of a manifest log. You take some blocks from the very end of this linked list. You see which events from those blocks are still present in the current version of the manifest, and you write those events in a new block in front of your manifest log linked list of blocks. And because some events are no longer necessary, in general, you will write less blocks than you need to. Okay, that was a very, very long-winded introduction, a lot of recap today, which is actually good. But let's get to the new stuff. Okay, we'll be looking at, okay, now it's not schema, it's manifest log, and we'll be looking at compact. Okay, compact. Compact is asynchronous operation, as usual. As every asynchronous operation in Tagabitl, it takes a callback as a parameter. The task of this compact operation is to do exactly what I have described right now, to read some blocks from the tail of the manifest log, figure out which events are still necessary, and write only those events in a new block from the front. Okay, so the first thing we need to figure out is that we need to figure out how many blocks we want to compact. And there is actually some pretty interesting math somewhere here. I wonder where it is. Oh, maybe it's actually not in this. It should be there. Okay, how do we set this? Okay, yeah, maybe this is not in the current version which we're looking at, but there was actually like, you know, there is like this question, like, okay, you want to compact some blocks, but like how many blocks do you want to compact? And the idea here is that on the one hand, you want to prevent your manifest from growing infinitely. On the other hand, you actually don't want to run compaction too frequently, because if you run compaction too frequently, you'll be observing that actually, hey, most of the events from those old blocks actually survive in the new block, so you don't end up like, you know, freeing that much space. You just like, you know, rewrite data again and again. So in the version of the code on the main branch, there is definitely some smart code which computes like the exact amount of blocks we need to compact. Okay, now we are going to quote mutate data structure. Mutation is an allocation. So we need to allocate our new blocks. If you recall from the video about free set, one aspect is that the API requires that before you allocate things, you actually have to provide an upfront upper bound on the number of grid blocks you might allocate. That is required for making a free set work deterministically in the presence of concurrency, which is something we'll understand better when we get to a real compaction. How many blocks we might want, how many blocks we need to allocate? Well, in the worst case, you know, you read n blocks from the end of the manifest log, and actually we figured out that, hey, no events can be eliminated. Those blocks needs to be appended to the head of the manifest log as is. So the worst case is that we write the same number of blocks as we have written. So that's why we say, okay, worst case is we didn't compact anything. But then, you know, like this compaction is like not running in a vacuum because, well, the reason why we want to compact manifest log is that we actually are appending events on top of this manifest log, and well, we want to prevent it from growing too much. So there is also certain number of events which have been appended since we last run compaction and which are currently in memory. And presumably, we actually would want to write all those events to disk as well. So we also append how many blocks how many new blocks we might create. Okay, then let's see what happens next. As usual, we okay. So I guess as usual we remember our callback, and I was thinking that actually, okay, so now we'll like go and read this first block we want to compact, but actually I guess first we'll deal with this thing where we have like some new events. So we like first we'll write the new events we have. Question: is this manifest log compaction done at the same time as the table compaction? Okay, so this is something I kind of like, you know, deliberately not disclosing yet, because we are like not that high to understand how compaction is actually scheduled. But let me give like the rough idea like when this happens in time. So traditionally, compaction is a fully background process in databases. So you have some separate thread which periodically goes and looks at your data file and like tries to like compact things down. And usual operations with database, appends and reads happen concurrently to this compaction process. this kind of looks like a reasonable, obvious architecture because, well, compaction logically is independent from mutation, so you could run it in parallel. That potentially gives you more performance because you exploit parallelism. Potentially this simplifies the code because, well, you can think about those two processes completely orthogonal. But in practice, there's there's one problem in that although compaction and normal operation are logically independent, physically they are very much not independent. There is only a certain amount of disk read and write bandwidth. And if it so happens that compaction is compacting something, and then you want to append something to the database, that mutator process will be competing for disk I/O with that compaction process. So for us in TargetMiddle, we actually didn't go with that background thread solution, and instead our compaction is deterministic and just in time. So when a database processes a new request, when it processes a new prepare, it makes sure to do just enough compaction work right at that point so that it can accept the next request. This is so-called compaction pacing. We try to spread out compaction work across normal processing so that after every bit of useful work, we do a deterministic small amount of compaction work. This, how exactly this is done is a little bit complicated. But basically, there is a cycle of 32 prepares. So every 32 prepares accepted by the database, we run a full round of compaction. And at different bits of these 32 bar, we do different compaction operations. And I'm not exactly sure when we run ManifestLog compaction, but because it says half bar append blocks max, it looks like we run ManifestLog compaction twice during this overall compaction interval. So actually we could take a look at where is this code. So this is called, okay, yeah, that is the answer. So our overall compaction interval, which is called LSM batch multiple, our overall compaction interval is called LSM batch multiple, and when the current op is divisible by half of that, we do and run compaction. So yes, it is compaction for ManifestLog is plugged into the same life cycle as compaction for tables, but physically it runs way more rare because, well, that's actually just less data there. I'm not sure, maybe I'm not sure how important it is to run it every half bar. Maybe it could be run more frequently, maybe it could be run less frequently. I don't fully understand whether there is a physical limit there or where we are just tweaking some constants. Okay, so it seems that the first thing we are going to do is to write the blocks with fresh changes which were accumulated in memory. And that seems okay. Let's see how it works. So we have a number of blocks which are currently in memory, which were filled with new events. then we actually, yeah, this is actually fun. This is like one example of concurrency. So you see, we have multiple blocks which might be filled. Okay. So I wonder what is this? What is like the total number of those blocks? Half bar buffer blocks max. Okay, yeah. So kind of like we, as usual, like we always like have like an upper bound of like maximum number of blocks we could have created in this half bar. So when we flash them, we run them, or we write them all to disk concurrently. So for every block here, write spending. Okay, yeah, I guess write spending like tracks like the count and like index of blocks we need to track. So we just go fetch the block. Presumably by this time the block should be complete, and we pick the write we have, which is again useful thing, something which I repeat on like every episode, that because we have static memory allocation, concurrency is refighting the data structure. So you can figure out what is the amount of concurrency looking at the amount of memory we allocate. So for these writes, we allocate this amount of memory, so exactly the amount of blocks, and and this gives you like clear answer of like how many concurrent write operations we can be doing. Okay, so we just go and write this block to greet. I guess it's interesting that we actually don't use a reservation here. Okay, this is okay, yeah, this is something I don't understand. If we look back at the compaction, I kind of like explained to you that, okay, we allocate all the blocks that we want to compact, because we might not actually be able to compact anything. And then we allocate all the blocks we want to append. But apparently, when we go to the flash, the blocks are already allocated, because remember, blocks also include their own address, just so that you can detect misdirected writes. And I don't see in this. Let's take a closer look here. So okay, yeah, we create reservation, we do a flash, we don't use reservation here, and I don't think we use, we don't seem to use reservation here. So by the time we get here, these blocks should already be allocated. Okay, so that actually means that I actually don't understand why we allocate that many blocks. Okay, that's where do we actually use acquire block? Okay, we use an acquire block and in acquire, and we use acquire block in append internal. Okay. So at this point, I guess I'm thoroughly confused. So let's continue. Maybe hopefully I will get unconfused. Okay. So anyway, we schedule a bunch of write blocks calls. They have the same callback. This is another like pattern of concurrent programming where you don't have async await. When you want to join a number of concurrent operations. So this is usually done via some sort of a counter. So here, when we schedule this concurrent operation to run, we increment write pending. In the callback, we decrement the write pending. When this write pending reaches 0, that means that, hey, all concurrent operations actually were done. So let's see how this whole thing flows further. So when we call flash, we use compact next block as a callback. This callback goes into the write callback, and presumably in the flash down, we'll go and call the write callback. Yeah, we fetch write callback, and then we call it. That write callback, I have already forgot what it was, so let's take a look again. That write callback was compact next block. Okay, yeah, so at this point, we have written all the new blocks, and I think we haven't used any reservations yet. So at this point, the amount of reservations should be exactly this if I'm reading the code correctly. So one of the two things will happen. Either we will use these extra reservations for something, or we will not use them, in which case I think that would mean that we have a bug here, and actually we don't, like, those are extra reservations which are not required to be filled. Which actually would be a fun, I guess that would be a really fun thing to do, to instrument our reservation so that, like, it logs when it is forfeited with non-zero, to make sure that every reservation we reserve actually sometimes can hit 0, so that our bounds are tight. Okay. So, finally, we get to the compaction proper. We have the target number of blocks that we want to compact. We take the checksum and the address of the oldest block, and we go and read this block. And again, like, this is something I will emphasize again and again. Like, this is beautiful. This read block will try to read block from disk, but it might be the case that the block on the local disk is corrupted. Like, there is some bitrot there, checksum doesn't match. In which case, transparently, this thing will go and fetch the block from some other replica. And this is only possible because we guarantee that ManifestLog blocks are identical across replicas. And kind of like this entire free set reservation setup was exactly to enable this kind of transparent recovery. So anyway, we read this block. Okay, what do we do next? Well, first of all, we kind of like say, okay, this block is no longer part of our manifest. I guess this should be specified more explicitly. So again, it's always like, actual data lives on disk, but you have some sort of a shadow of this data in memory, some kind of like, not the entire data, because of course, like, if you could fit everything in memory, then you wouldn't use hard drive. But you want to keep like this summary. And in the case of ManifestLog, we keep the list of all blocks in memory, but the actual blocks are on disk. So after we have read the block, we say, okay, so now we logically remove this block from our list of ManifestLog blocks. Now, we need to actually go and parse this block and figure out which events should be appended. To parse this block, we use schema definition from a schema file. And manifest node should be storing a bunch of table infos, which is just table address plus level plus removal or insertion. And I guess the core, the core method here is tables, which takes a block and casts its body to slice of tables. Again, like super simple code. And I guess like another like important thing here is like previous, because this is the linked list. So it is important that you could refer from the block to the previous one. Okay, so we get the block. We fetched the tables. We sliced the tables by the amount of okay. Why do we do it this way rather than just this way? I think those should be okay. So it sounds like this one is actually redundant because the length of that one is like already this. But anyway, okay. So now we need to deal with this event. Okay, so it cannot be reserved if this is insert or update. I think what we do here is we check whether this okay, yeah. We check whether, so this is insert. That means that like at that alt point in the block, the table with that address was actually used. We need to answer the question, are we still using this table? If we are still using this table, then we need to move that insert from the tail of the ManifestLog to the head. And this set of currently used tables is exactly this table extend map. So when we like mutate ManifestLog, we update table extends to say, which kind of like, okay, so you kind of like think of table extends as a hash set of the tables which are currently exist in the LSM tree. And kind of like the key in this hash set is an address of the block. And I guess, the address of the index table and what is the entry index? Okay, I'm somewhat suspicious there because, okay, could this be buggy? Because, okay, so like, obviously like one way you can like key the table is by the address of its index block. But that is not enough, because what could be is that you add the table, then you remove the table becomes free, its index block becomes free, and then that index block gets allocated for an index block of another table. So you actually, like, the index block is the same, but the table is different. It seems that we additionally key this entry with, this really looks like a bug to me. Okay, maybe I'm misunderstanding something. So we additionally key this address. Okay. No. There is no bug. It's just me being stupid. So like this Okay, yeah, right. So the key in the table extent is the address of a table. The value is the address of a manifest block and the index in that manifest block. So yeah, it's like all those addresses as well, the address of a manifest block. So we essentially say that, okay, this address points to a table which is a part of LSM tree right now. And that address was inserted into the LSM tree by that particular ManifestLog block. So what we can, when we do compaction here, we might see that, hey, this address exists, but it was actually inserted by a different block than the one we currently look at. In which case, it means that, hey, this table was shadowed, so we can drop it. Otherwise, if this table is there, okay, kind of like, let me rewind this and try again to be less confused. Okay, so we look up in the hash set of active tables the tables with this particular address. We can get nothing. That means that this table is definitely dead right now, and we can just drop this event. Otherwise, this table is live. And we need to disambiguate between two cases. This is actually like the same table, or it is a different table which just happens to share the address of the index block. And for that, we look at which entry in the manifest log created that table which is currently live. If that entry is, well, the current entry, then this insert or update record survives compaction, and we append it. Otherwise, we like mark it as a free. Finally, yeah, if this is a okay, it's actually okay. Yeah, okay. This is funny. So if this is a removal, then we can safely discard it, because like we compact from oldest blocks to the newest blocks. So if this is a remove, then before this remove, we had an insert. Now, because we are compacting the remove, we have already compacted this insert. So either this insert was dropped, or this insert was actually moved in front of the remove. In either case, we can safely discard the remove now. Okay, so let's take a look at this append internal. I guess it should do, okay, yeah, so it should write into internal in-memory buffer with like the block which we are currently fitting. So we see that if we don't have okay, yeah, right. So first we need to make sure that we actually have this block. Apparently we acquire the block the first time, so when the manifest is completely empty, or I think this close block thing should tail call to acquire block as well. It should call acquire block, I hope. Otherwise I don't understand this. Well, it doesn't do this. Okay, then let's okay. I kind of like fail at like looking at this and explaining. So let's try to read this more closely. Okay, so what is entry count? Okay, yeah, this is not at all number of entry, this is number of entries in the open block. So yeah, if we have 0 entries in the currently open block, that means that we need to acquire a new block. And that goes to our reservation, which we have created, and asks the grid to allocate a block out of that reservation. We get back a block address, and then like this block has corresponding in-memory data. So like we know like we kind of like reallocated data on disk, and now we need to fill this data. Obviously, before data goes to disk, we need to fill this data in memory. And for in memory, we actually manage that memory ourselves. We have the array of blocks. So we take the last one and just says, okay, this is now allocated block. This is the address. This is all the other fields which we can fill here. Okay, so after this line, we do have a block allocated. That is our block. So when we allocate the block, we like take it from the tail of list of blocks we have. So it is the same block. Table, okay, yeah, well, tables entry, okay, right, that makes sense. So we want to append to this block. We know the index of the list, the index of event in this block. This is exactly what entry count is counting. I guess we should, yeah, we'll be incrementing it here. So we go and write our table info, which is table insert, remove, and the level, into that place on the block. So we've already seen this tables function, but let's take a simple, a quick look again here. So just take the block, take the body of the block, so cut off the header, and slice it by the number of tables this block could have multiplied by the size of table info, and cast that to the array of table infos. And then we go to the entry count index there and write the table. Okay, perfect. Then we update that table extend data structure. So we say that, okay, so now the table with this address is active. And it is stored in this block. Again, we might have seen this table already, in which case the label event might be insert, or it may not be insert. But if this wasn't, okay, label event, okay, yeah, right. This is either insert or update. So if this is maybe insert, that means that, okay, yes, this is either insert or update. I guess at this point I need to explain like why we distinguish between inserts and updates, because well, update is removal followed by the insert. And I think that has to do with the way we read the manifest block. Because well, actually, okay, yeah. Okay, I'll be honest, I actually don't remember exactly why we cannot encode update as just an insert and remove pair, but I think that basically boils down to like when we read ManifestLog, when we open the data file, it kind of like allows us to easier understand which is the latest event, because we only care about the latest event. Okay, anyway, we like updated our table extent. Otherwise, if this event is removal, this address is no longer pointing to the address on active table, so we go and remove this table. Then we increment the number of the index of the event in the current open block, and if we figure out that, hey, the block is now full, we go and finalize our block, which means that we basically set the checksum. So the core, yeah. So this is like the core thing. We fill the block, so now we can actually freeze it and we can checksum it, which is exactly what we are doing here. Well, yeah, and we also push it to the list of the blocks which belong to the manifest. Okay, so coming back to our compaction thing, because remember, this is all compaction. Yeah, this is compact next block. So we have read the last block of the manifest. We processed all the events which are no longer needed, we just drop them. Other events we appended again to our ManifestLog, which ended with events being in front of the thing. Okay, then we assert that we actually created no more blocks than the amount we compacted, and then we go and, well, again, another one thing, now that we have compacted this block, we can actually mark it as a release. So we call grid release, which internally calls that freeset release. And the reason why we go to the grid rather than to the freeset directly is because, well, this grid also manages the cache of the blocks. So the fact that the block is released is pretty significant hint that, hey, we no longer need to cache this block, so we can evict it. Okay, and then we go and compact the next block. Again, the number of blocks we need to compact is tracked by this compact blocks variable. So I think, where do we? Oh, right. Yeah, we decrement it here, because it's kind of very useful pattern is that if you have asynchronous loop, which is controlled by some variable, then it's good if the exit condition and the increment condition are actually physically in the same asynchronous function. Okay, so we go and read the next block from the tail until we read all the blocks. So after this thing, we have freed some amount of blocks, and well, actually, let me show this again. So after this whole loop, we released some amount of blocks, and we created some amount of blocks in memory, but we haven't yet written those blocks. And I think that should basically be it. So when we call compact done callback, and that just calls the callback, which is really nice because we are almost at an hour, and again we managed to cover somewhat well specified chunk of Target in a single episode. So let's recall this, although again it's kind of not really all that much to recall, because that was really episode focused on let's look at the code, let's look how we actually do synchronous programming. But nevertheless, recap. We are looking at ManifestLog compaction. ManifestLog describes the structure of LSM tree by storing the resulting structure as a series of individual insert and delete and update events for particular tables. So ManifestLog stores insert this table into that level, that table into that level, etc., etc., etc. And there is some removals. When you kind of execute all those events, in the end you have a picture of which level contain which table. On disk, this manifest log is represented as a linked list of blocks, where each block stores an array of events. To prevent this array of events growing infinitely large, we periodically run compaction, which means that we take a certain amount of blocks of the tail of a manifest log. We read them in memory. We look at each event in those tail blocks and decide whether this event still makes sense. That is, that event is an insert and the table which was inserted back then is still active. And if that is the case, we just move this event to the front of a manifest log. If that is not the case, we just go and drop the block, drop the event. Param-pam-pam. What I was saying, I guess that's basically it. What was happening with grid blocks there? When we have read all the events from the tail of manifest log, we just go and mark that block is released because it is no longer needed. And conversely, when we filled a number of blocks with events, we go and flush those blocks. We go and write those blocks to disk, which I think is it. And one open question is why when we, okay, sorry. One open question is why when we compact, we allocate we reserve this many blocks. I think this is a bug. I think this one actually isn't required here, but maybe I'm wrong. So I will take a closer look and maybe submit a pull request. So that's it. Again, this lecture was a little bit more of, hey, let's dive right into the code, rather than, hey, let's draw pretty pictures. But I hope this is also useful and interesting. And please join me next week on Thursday at 5 p.m. UTC, live on Twitch, when we will be talking. I guess we'll be slowly inching toward, like, the real compaction, real LSM3. But perhaps before that, we'll need to cover our ORM, our forest. We'll see. And if you, for some reason, miss 5 p.m. UTC on Twitch, no problem. All recordings are on YouTube, on TrackAsBeetle YouTube channel, under the Iron Beetle playlist. So thanks again for watching, and see you next week. If I actually manage to finish this recording.